What I have for you here today is a talk focused on treatment of divalent metals, specifically in soil and groundwater. And I hope to work through it in 40 to 45 minutes, leaving time for comments and questions. So before moving into the talk, I wanted to kind of outline my perspective for this presentation. The goal of the meeting today is to review at a fairly high level some of the factors that are important in selecting an effective approach to treating soil or groundwater where divalent heavy metals are your targeted contaminants of interest. The presentation has been put together under the assumption that some or even many of the attendees are newer in the remediation field and are not experts or not familiar with treatment of metals in soil and groundwater. In keeping with that assumption, I'll be covering some pretty basic material, so I apologize for those of you who don't need that kind of basic review, but I will do that. And then finally, I'm not going to spend a lot of time on detailed case studies. We have those, they're available to you. If you'd like them, reach out to me directly or contact your local Evonik representative. But instead of a detailed case study, I'll just show three very brief project snapshots at the end. So, an agenda, what are we hoping to cover? There's a nice picture of some of the kind of metals that we're looking to create by treating the soil or groundwater. Really what we're trying to do is promote precipitation of these soluble heavy metals as divalent metal sulfides. So we're going to look at the basics, do some definitions, cover some technical terms, give examples of how the precipitation reactions happen, talk a little bit about the fact that what we're looking to promote with our reagents is a natural process, and we're just looking to speed it up, make it more profuse, and make it go to completion more rapidly. We'll talk about the conditions needed to achieve that, the importance of pH and EH. We'll look at these phase diagrams or Courbet diagrams for some representative divalent metals, then move on to talking about how we create those conditions with our Metafix and Geoform reagents, talk in fair detail about their composition and what mechanisms they promote, and how their design helps to reduce susceptibility to rebound, how we can sort of lock these precipitated metals up in a way that they won't come back into solution. Then go on to show one example of a detailed bench scale treatability study to illustrate the kind of removal we can achieve, and then look at the three brief project shots. And if I speak quickly enough, that'll leave time for questions at the end. All right, moving on to definitions. So really what we're doing in removing these divalent metals is trying to promote four mechanisms. Precipitation is the first one, and this shouldn't need a definition, but really what we're doing is moving a soluble metal into an insoluble or much less soluble form by creating an environment that is saturated from the perspective of that metal and something that it likes to precipitate with. And the perfect example is loading up the environment that contains dissolved lead with sulfide in the form of HS- that lead likes to precipitate with, that falls out of solution as the almost totally insoluble metal sulfide galena, lead sulfide. Co-precipitation is similar, except there's kind of a two-step process. Your divalent metal attaches to something else, typically that has a charge on it, and the combined two fall out of solution with another metal. And a perfect example of that is how zinc attaches to an iron oxide and then precipitates out as zinc iron sulfide. Adsorption, of course, is just attachment of the metal to a surface of some type, typically along the lines of ionic charge. But another type of adsorption, one that we promote with one of our Metafix formulations, is adsorption of organometallic compounds to the activated carbon in the metafix reagent. And good examples of that would be removal of tetraethyl lead or methyl mercury by binding it onto the activated carbon, since these organometallic metals don't like to precipitate according to the normal sulfide precipitation or any other normal precipitation method. Occlusion is something that I'm very big on, and I think is a real strong advantage of the approach we use with these long-lasting reagents. And by occlusion, I mean encasement or encapsulation or locking up of the freshly precipitated metal sulfides by continuously laying down additional layers of either the same metal sulfides or actually profuse precipitation of iron sulfide, which is very low in solubility, and it's kind of locking these up by putting them underneath layers of other insoluble materials, and that can prevent resolubilization when EH conditions change, or if you're in an aquifer that tends to acidify. And then I'll use the term biogeochemical a number of times, and I just wanted to add that to the definitions. It's something that we typically think of for chlorinated organics, but it is effective for certain of the metals, because as you're creating these iron sulfides, for example, with our geoform reagents, you're trapping and encasing dissolved metals, and that's the use of biogeochemical remediation technology to remove inorganic compounds in a slightly different way than it's used to dechlorinate TCE and similar chlorinated VOCs. All right, let's look at these divalent metals and what the actual chemistry is that we're looking to promote. So here are three examples for using lead as an example of precipitation reaction. So the first one there in black is sulfide precipitation. This is the major one that we're looking to promote with our metafix and geoform reagents. Dissolved lead, aqueous lead, ionic lead, Pb2+, will fall out of solution when you get the concentration of sulfide high enough, and if pH and EH conditions are right, that will fall out of solution as the mineral galena, PBS, that has very low solubility. There you can see the solubility in water under standard conditions, 10 to the -6 micrograms per liter. So way, way under MCLs or TCLP standards. Carbonate precipitation, same thing here, example with lead showing how lead will precipitate with free carbonate to produce lead carbonate. It has higher solubility than the sulfide, but it is lower than the MCL for lead. And then hydroxide precipitation. This is a high pH approach, typically mediated with things like magnesium hydroxide or other high pH reagents to produce lead hydroxide. And take a note there of the solubility. It's several orders of magnitude higher than either the lead sulfide or the lead carbonate, and in fact it's higher than the MCL for lead, so not necessarily a very good way to go at treating lead in groundwater. A little bit more detailed look at the same kind of thing without the equations. Here's a list of the common divalent heavy metals that we are often required to treat. What are the major dissolved species? Typically the cation, the divalent cation, as well as some organically bound versions of these metals. Too complicated, there are too many of them to actually list them out, so let's just call them organometallic compounds. And some of the metal hydroxides are actually having a substantial water solubility, so they are dissolved species that could cause a need for treatment if you need to achieve MCLs. Next column shows what are the common remedial standards, MCLs or other regulatory standards that I've been able to find. And then looking at the relative solubilities of the sulfide precipitate, the carbonate precipitate, and the hydroxide precipitate. So this kind of reinforces what I said on the previous slide using lead as an example. In all cases, the lowest solubility precipitate for these divalent metals is the sulfide. So it's the best way to go if you can do so. Carbonate and hydroxide, they are having higher solubilities, and depending on the metal, one or the other might be the least applicable way based on what their solubilities are relative to MCLs or other standards. Another way of looking at this, and perhaps even more important, is not the absolute solubility under standard conditions, but the impact that pH has on the solubility of the two major groups of metal precipitates, and that is the hydroxides and the sulfides. So here we have this nice figure from the EPA document referenced there, and a couple pictures of the lead sulfide and the lead hydroxide, galena and cerussite. But really what I'd like you to note and remember is that in addition to the solubilities of the hydroxides being several orders of magnitude higher than the solubilities of the sulfides, look at the shape of those solubility curves for the metal hydroxides. They are typically at a minimum in the alkaline, or at least in the slightly alkaline range, but they have minimums at a very narrow pH range. And once you get outside of that very narrow pH minimum range, either higher or lower pH, their solubilities go up dramatically. And perhaps most relevant for our groundwater treatment approaches is as you move into the slightly to moderately acidic range, the solubilities of these metal hydroxides go up sharply and go well above the MCLs. So in contrast to the metal sulfides, look at the slope of the solubility curves. They're much flatter, the absolute solubilities are lower, but they're much less significantly impacted by changes in pH, particularly by acidification. So even when you get into the acidic range, the metal sulfides retain solubilities well below your MCL or other relevant remedial standards. Okay, this beautiful figure from Professor Kirk at Kansas State University kind of is good to get our thinking into what sulfide precipitation is all about and how we can mediate that in groundwater or soil. So what he's drawn here is where you have an electron donor in an aqueous environment, you will have microbial growth, heterotrophic bacteria consuming oxygen, then moving on to consuming the nitrate, then moving down the redox ladder, moving on to reducing sulfate, converting that sulfate to sulfide that stays in solution. If you're at neutral or near neutral pH, it won't volatilize as H2S. You'll have a lot of HS minus. At the same time, as redox potential falls, iron oxide bearing minerals will be reduced energetically, releasing ferrous iron, and then iron reducing bacteria will get involved as well, and they'll begin to reduce these minerals and release more ferrous iron. Now you have an environment that is rich in iron and free sulfide, and that will precipitate as iron sulfide. If you have divalent heavy metals of other types, they will also precipitate under that condition, or else be trapped in the iron sulfide as it precipitates, and you end up with iron divalent metal sulfides as well. This is a natural process, and I've got a few points here on the left from the excellent paper by Rickard and Luther. And if you look at some of these points, they estimate that each year something like 150 million tons of sulfate are reduced in sediments around the world, reduced to sulfide, and that most of this is microbial sulfate reduction. And as a result of that, there's a production of somewhere like 5 million tons of iron sulfide pyrite in sediments every year. So the point I'm making with all of this is we're not looking to promote chemistry or biochemistry that is difficult to mediate or finicky or that requires inoculation with special bacteria. These sulfate reducing bacteria are everywhere. If you can get a suitable electron donor that lasts a sufficiently long period of time and get the other things you need, phosphorus is particularly important because sulfate reducing bacteria are dependent on phosphate for their enzymes. You can mediate this reliably and powerfully. So the message here is natural process, we're enhancing it. In order to understand where we need to go to promote this kind of divalent metal sulfide precipitation, we should look at some phase diagrams. And before looking at phase diagrams for things like lead and zinc and nickel, let's make sure we understand what phase diagrams are actually telling us, what they can and cannot tell us. So here's an example of a phase diagram that has a well going down into the subsurface. And there's a number of important points here. So each region between the lines illustrates the EH-pH zone where a given species, in this case iron, is thermodynamically stable and therefore is likely the most abundant species. So let's look up here in the upper left. High EH, oxic environment, and acidic pH. Under those conditions, you can have some ferric iron in solution. Moving down, having stronger reducing conditions, although still aerobic. If you have acidic conditions and slightly more reduced conditions, you will have ferrous iron. The horizontal lines indicate electron transfer. That's pretty clear here. Ferric iron converted to ferrous iron. That's an electron transfer, a reduction. The vertical lines indicate a proton transfer. So when you move from, for instance, ferrous iron to iron oxyhydroxide, FeOH3 here, that's a proton transfer. When you go lower here and you have these sloped lines, for instance, the line of demarcation between ferrous iron and iron sulfide or pyrite here, that's a redox equilibrium involving hydrogen or hydroxide ions. One of the really interesting things and nice thing about this particular phase diagram is it allows you to understand how the concentration of dissolved iron impacts the stability regions. So over here on the right at the top, let me get this this pointer, laser pointer. Okay, up here you have iron at 10 to the -5 concentration. You can see where the line of demarcation where ferric iron goes to the iron oxyhydroxide. But as you increase that concentration of dissolved iron all the way up to 10 to the first, that place where the precipitation begins to happen, where the conversion of dissolved iron into the precipitate iron oxyhydroxide happens at a lower and lower pH. And that's true for most of the dissolved species. Precipitation will happen at either higher EH or lower pH when you increase the dissolved concentration of one of your solutes. So phase diagrams can tell us what are the stable species and where in the pH-EH equilibrium they like to exist and where they're stable. On the other hand, phase diagrams don't provide us with any information about kinetics. So they don't tell us how quickly these different species will form, and they don't tell us how quickly these different species will unform or dissolve or come back into solution after they have been formed. Now, this is one that people don't typically look at, but it's useful to develop a better understanding of sulfide chemistry in water. So if you look at the phase diagram on the left, and you look at that, you might think that that vertical line at about pH 7 tells you that on the right side of that, all of your sulfide will be HS minus, the ionized form, and on the left side, it'll be H2S. And above that line, you'll have only sulfate. This, of course, assumes there's no enzymes involved. This is just chemical equilibrium. But if you look at the diagram on the right, the impact of pH on speciation of sulfide in water, what you'll see is that that line at pH of 7 in the phase diagram tells you that there you actually have equimolar concentrations of H2S and HS minus. So you have a range around that where you will have both. You'll have an equilibrium. The farther to the left you go, more acidity, you'll have more H2S. The farther to the right you go, more alkalinity, you'll have more HS minus. So that's important to understand when looking at phase diagrams, that it's not a sharp line of demarcation. These are actually equilibrium, points of equilibrium. Now let's look at the same thing, the sulfate-sulfide phase diagram, and that zone here where you have some form of equilibrium depending on concentrations of the different solutes between H2S, HS minus, and sulfate. And then let's look at the iron in water phase diagram. So at this level, you have HS minus and H2S. Both of them will react with iron, although an interesting point is that HS minus is more reactive. It's a better electron donor than H2S. So all things being equal, you're better off to be at neutral pH or a little bit higher. There's a couple of reasons for that. HS minus is more reactive, HS minus is not volatile, and HS minus doesn't have a bad odor like H2S does. So a number of reasons why it's better to be in the HS minus range. Looking at the iron phase diagram, in that same area where I've drawn this box in, it's where pyrite likes to exist. So in the same area where you have a lot of sulfide, and particularly the more reactive type of sulfide, you have a region where iron sulfide, pyrite, is stable and will like to form and will like to stay in its solid, insoluble, precipitated form. So good. Now we have a bit of an understanding of how sulfide and iron relate to each other and where they would like to precipitate together to form iron sulfide. Let's look at some of the divalent heavy metals, and I've applied that same kind of sweet spot here in this box on the pH-EH diagram for lead. And what this shows you that is in that same region where free sulfide and iron will precipitate as pyrite, free lead or dissolved lead, ionic lead, will want to precipitate as lead sulfide, galena, which has extremely low solubility and will be stable in this range of pH-EH. So it works. The iron sulfide condition that we create with our reagents will also work very well for precipitating galena. And here you have the standard conditions and the reference where that diagram was pulled from, and a couple nice photos of lead hydroxide and lead sulfide. Looking at another one of the divalent metals that we commonly need to deal with, cadmium, same thing. That same sweet spot will work well for precipitation of cadmium. A couple interesting points. CD2+, of course, is the dominant soluble form in groundwater, and it will precipitate either as a carbonate or as a sulfide. Cadmium carbonate has fairly low solubility, and it has pretty good low solubility so long as your pH stays above 7, but it becomes increasingly soluble even above the MCl as pH moves into the acidic range. On the other hand, cadmium sulfide, greenockite, is stable over a very broad range of pH and EH conditions, well below the MCl, and does not come above the MCl even if you get fairly strong acidification. Cadmium hydroxide has low solubility, but is only stable above a pH of about 12, so kind of irrelevant in terms of treating cadmium in soil or groundwater. Also note substantial dissolved cadmium can be present in organometallic forms, particularly in environments where you have a lot of dissolved organic carbon. Over time, bacteria process the carbon and deal with the cadmium. They try to detoxify the cadmium by attaching a side chain to it. And then finally, we'll just look at one more, nickel. And once again, these things are very consistent. All of these divalent metals will precipitate in the same area where iron sulfides will precipitate, and they will fall out of solution as divalent heavy metal sulfides. In the case of nickel, it's called viacite. Another interesting thing about nickel, kind of unique to nickel, is that nickel can be incorporated into layered double hydroxide minerals, and there's a large group of these. They're actually an important ore in the nickel mining industry called garnierite, and they're a phyllosilicate group, and that's what we've got illustrated here above the nickel sulfide line. So they're an important mineral in the environment. So we've established that if we can create an environment that has sufficient free sulfide and sufficient ferrous iron, we can precipitate iron sulfide. That's a good thing, particularly if you're precipitating heavy metal sulfides and you want to encase them or occlude them or lock them up. The question is, how do we create that condition and create it in a cost-effective, long-lasting way? So let's look at that. What do we need? We need to generate strong and long-lasting reducing conditions. How do we do that? Supply readily metabolized organic carbon and nutrients. Longevity is important, and because of that fact, we like to use processed plant fiber in one family of our reagents, geoform ER as an example, and we use lecithin in the geoform soluble reagent. We want to ensure an adequate supply of free sulfide, so we supply both rapidly and slowly soluble sulfate salts in our geoform reagents. This ensures that you will have a long-lasting supply of sulfate to be reduced to sulfide. We also need to ensure an adequate supply of phosphorus because sulfate-reducing bacteria are dependent on adequate phosphorus for that first step in the sulfate reduction process. So one of the nice things about the processed plant fiber is that it's rich in organophosphorus compounds, and the same thing with lecithin. Lecithin is mainly composed of phospholipids. As the name implies, they contain lots of phosphorus. So we address that essential need for phosphorus by sulfate-reducing bacteria with the carbon substrate in our reagents, so we don't have to add inorganic phosphorus. We want to ensure an adequate supply of ferrous iron, so we supply ferrous iron, soluble ferrous iron salt. We also get ferrous iron from the aquifer by pushing the redox potential down, as I showed you in that very beautiful graphic where iron will come out of the matrix as ferric iron minerals are reduced and ferrous iron comes out. And we also provide a long-lasting source of ferrous iron in our high surface area microscale ZVI. And that ZVI, in the presence of carbon fermentation, will release more ferrous iron because the acidity produced by carbon fermentation in the form of volatile fatty acids, acetic, butyric, propionic acid, when they contact the surface of the iron, you get more rapid corrosion and therefore more release of ferrous iron. And the balancing of the alkalinity that ZVI creates with the acidity from carbon fermentation And the way we structure our reagents, the composition, the percent by weight of the carbon versus the iron, allows us to maintain pH in that neutral range without pushing pH way up as iron alone would, or pushing pH down as carbon substrates alone would. So that's how we aim to do this. Now let's look at in a fairly granular way, let's look at the reagents we're speaking of for treating divalent heavy metals. The first three are our Metafix family of reagents. They have one thing in common. All three formulations, I3, I6A, and I7A, are all based on a blend of reactive minerals. These reactive minerals provide they're fine-grained powders that provide slowly released ferrous iron and slowly released sulfide, and also have surface charges, so they will concentrate reactants at their surfaces because of charge interactions. These three Metafix reagents also contain a substantial amount of microscale ZBI that everyone understands what's going on with that. It's a powerful reducing agent, produces some alkalinity, and will slowly release ferrous iron over a period of years. One of the Metafix formulations adds to that basic blend slowly soluble carbonate source to promote precipitation of those metals that like to precipitate as a carbonate. The other one contains activated carbon, I7A, in order to ensure removal of organometallic compounds like tetraethyl lead or methyl mercury, or even though we're not talking about arsenic today, there are a lot of organoarsenic compounds. So that's the reason we have the formulation Metafix I7A. Now, they contain no organic carbon of any type. They're strictly inorganic reagents. Now, looking at the geoform reagents, both geoform ER and geoform soluble contain zero valent iron. Geoform ER contains granular ZBI in the range of about 50 to 150 microns. Geoform soluble contains very fine 5-micron iron. The objective here is that geoform soluble can be put through a well screen or for sites where you want to do that type of emplacement. In addition to the ZBI, both of them contain slowly released, long-lasting organic carbon, quick release, rapidly acting organic carbon and nutrients. They contain soluble sulfate to serve as a source of free sulfide after it's reduced by the sulfate reducing bacteria. They both provide dissolved ferrous iron, and they have pH buffering or pH balancing ability. So these will get us into that range that I've been illustrating on the phase diagrams for sulfide, for iron, and for the divalent heavy metals if we get them in the right way. So to review, and I won't go on this line by line, but just to say the formulation of these reagents will give you the reducing conditions you need, the ferrous iron you need to promote profuse precipitation of iron sulfides to lock up the precipitated heavy metals, a good environment as far as pH and free sulfide to precipitate divalent metals as divalent metal sulfides, which are almost insoluble, and they're pH balanced so that you won't go outside that optimal range. And in addition, when we combine our Metafix with the geoform reagents, fermentation or metabolism of the organic carbon gives us these simple, low molecular weight organic compounds like VFAs that sulfate reducing bacteria need in order to do sulfate reduction, and the phosphorus that's essential to good activity of sulfate reducing bacteria. These reagents together help you to create that environment that will ensure good precipitation of the divalent heavy metals as divalent metal sulfides, and that they will be encased or occluded or locked up by continued precipitation of iron sulfides. And here just a little bit to highlight and kind of so it'll stay in your mind what I've said a couple of times here about the sulfate reducing bacteria. There's no need to inoculate. These bacteria are broadly distributed, something like 40 genera and more than 100 species have been identified. They will reduce sulfate to sulfide under a fairly broad range of reducing conditions and fairly broad range of pH conditions, so long as you can provide them simple organic substrates like VFAs, alcohols, or glucose, and as long as they have the phosphate that they need. And that's an important aspect because this first step, ATP sulfurylase, is dependent on a sufficient supply of phosphate because it's in the structure of this critical first enzyme. And here we have a nice picture of a biofilm of sulfate reducing bacteria on an iron particle. And then just to kind of reinforce everything that I've said before looking at some data, this is kind of the environment we're trying to create to have metal sulfide precipitation, as illustrated here, precipitating lead as lead sulfide or galena, and to promote occlusion, this continued laying down of iron sulfides on top of the precipitated contaminant, on top of the divalent heavy metal sulfides that we've precipitated. And we accomplish that by having a long-lasting carbon substrate up here at the top, that its fermentation, whether that's the phytic acids in the processed plant fiber or the phospholipids in the lecithin, these get simplified. They provide a good carbon substrate for the sulfate reducing bacteria. As they're simplified, they also release phosphate that can be incorporated into that first enzymatic reduction of sulfate to get lots of free sulfide. The iron in the geoform and metafix reagents provides alkalinity and slowly released ferrous iron to prevent undue acidification. On the other hand, the volatile fatty acids produced in the carbon fermentation prevent pH from going too high to ensure that the zero valent iron continues to release ferrous iron over time, which is essential for this occlusion step that helps to prevent rebound. So all of these things work together if you balance them properly and use the right kind of long-lasting reagents that will supply iron and organic carbon and phosphorus. How long will these iron sulfides that we like to make to lock up the heavy metal precipitates, how long will they last? Here from this CERDIP paper, some really interesting work was done with iron-coated sand, sand that had been chemically coated with FES. And if you look at this paper, there's the reference there, you can do some calculations and find out that they had laid down about 122 ppm of FES on the surface of a mineral sand, a clean sand. Then they packed columns with it and pumped water at 3 different pHs through those columns and used effluent ferrous iron concentration as a way to estimate how long it would take for these iron sulfides to be dissolved. And the long and the short of that is that after 60 pore volumes of groundwater had been pumped through these columns, only about 2.5% of the iron in the iron sulfide had washed out in the effluent. So what this tells us is that these iron sulfides will last for decades in situ, where you typically have pH in the neutral range, so that locking up or occlusion can be a very long-lasting safety net, so to speak, on your removal of the divalent metals. And that's the point I really want to make here with this slide. It's important to have long-lasting reagents so that you will get this continued precipitation of iron sulfides on top of the precipitated divalent heavy metal sulfides to lock them in, occlude them, encase them, and prevent rebound. So Let's quickly look at a little bit of performance data. Here's a bench scale treatability study done by Professor Cassidy in his lab at Western Michigan University. Doug Gray at AECOM was the project manager, and this was funded by Michigan DEQ. They had soil and groundwater from a site impacted with nickel. They used low flow pumps, upflow columns. They evaluated a whole number of reagents, and the highest performing reagent was in fact our Metafix reagent. And here's the performance data over 70 days of pumping through those columns. What you can see is that in the control column that was packed with soil from the site that had about actually, I should have addressed that. This is significantly impacted soil, almost 2,000 ppm of total nickel, SPL P nickel 33,000 ppb, and the groundwater itself had almost 3,000 ppb of dissolved nickel. In that system, pumping that groundwater through the solids alone, there was no retention, no reduction. What went in came out over the entire 70 days of pumping through these columns. Roughly 3,000 ppb of nickel coming in, 3,000 ppb of nickel at the mid-column sampling port, and about 3,000 ppb of nickel in the effluent coming out the top of those columns. In contrast, let's look at the column that received our Metafix reagent at a dosage of 2% by weight. Same thing, same soil, same groundwater, 3,000 ppb approximately of dissolved nickel coming in. But by the time that water got to the mid-column sampling port, much of it had been removed until we got somewhere after about day 40. That 3,000 ppb it had been reduced to well under 100 ppb, and then went down to even less than 50 ppb, between 40 and 50 ppb. And the same thing was true in the effluent, the outflow from these columns. So extremely good removal of dissolved nickel with the Metafix reagent in columns pumped at a flow rate of about 1.2 feet per day until day 50. And after that, it was reduced to about half that. But almost complete removal of dissolved nickel with the Metafix reagent. So let's look at some very quickly project snapshots. This is from a completed project in the Pacific Northwest, where soil mixing trench type PRB was installed using our Metafix reagent on its own, and site soil was the matrix to which it was mixed to create this trench type PRB. The PRB was aligned along the riverfront here at this site in the Pacific Northwest. PRB dimensions about 80 feet long, 3 feet wide, 15 feet thick, from 5 to 20 feet below ground surface. Dosage of the Metafix reagent in that soil mixing PRB 6% by soil mass. So it took about 24,000 pounds of reagent to create this PRB to cut off the metals from getting into the river. And here you have the performance data. The metals here, since we're talking about divalent metals, let's look at the copper, reduced from somewhere in the range of about 50 ppb where it started. There was a bump right after installation of the PRB, which I'm sure many of you have seen, disruption of the subsurface, but then continued reduction down to well below the remedial objective for copper of 12 ppb. And that same groundwater had really high aluminum, about 2,000 ppb of aluminum that was reduced to well below the action level for that of 750, and arsenic that started in the range of about 6 ppb and was reduced down to well under 2 ppb by the end point. You might say, what happened at 13 months? Well, that was a 1 in 25 year rainfall event at this site. So that was attributed by the consultant to flushing of metals from the surface as a result of that several days of extremely heavy rain. Another quick project snapshot, this one all divalent metals at an industrial site in the eastern United States. This was an injected PRB using a combination of our Metafix I7A and Geoform ER reagents. And here you have all the project details, temporary borings by sonic drilling, enhancement with pneumatic fracturing, bottom-up injection, then abandon the borings, 65 discrete intervals, just under 12,000 pounds each of Metafix I7A. Recall this is the one that has the activated carbon in it, and our Geoform ER, some flow K, and inoculation with SDC9. And very nice, and oh, sorry, I should point out, we're looking at this one, MW3A, for the performance data. So here at MW3A, we have quarterly monitoring showing very nice reductions in all the chlorinated ethenes, but we're talking about divalent metals, so let's look at that. Cadmium reduced to below the groundwater protection standard. Nickel was already below, but substantially reduced in addition to the fact that it was below the treatment standard. And zinc from almost 3,000 ppb reduced by more than 90% down to 250 and well below the action level. And concomitant with these changes or removals of the chlorinated ethenes and the divalent metals, we had a gradual increase in pH modestly and drop in ORP and over time. And then finally, a soil mixing case study. This was to remove leachable mercury at an industrial site that was used as a catalyst, where mercuric chloride was used as a catalyst, and it was to be developed for residential land use. The objective was a tough one, needing to reduce SPLP mercury to less than 1 ppb. The untreated control soil had SPLP mercury of about 35 ppb, total mercury of over 300 ppm. And the bench scale testing showed that either 0.5% or 1% of Metafix performed equally well and was able to achieve that 1 ppb for SPLP mercury. We then went on to a pilot demonstration, 50 cubic meter batches, several of them, to compare at larger scale with soil mixing with heavy equipment, 0.5% dosage versus 1% versus 2%. And while there was possibly a little bit better performance, there was no difficulty in achieving the 1 ppb SPLP with 0.5% by weight. So the consultant decided to go with the 0.5% by weight. The full-scale application involved treatment of several thousand cubic meters of this same mercury-impacted soil. 0.5% by weight of the Metafix reagent, added water to bring water content up to about 80% of the soil's water holding capacity. So the soil was quite wet, but there was no free water. We weren't creating a slurry. Reaction period was only 7 days, and all of that several thousand tons of this soil was treated to achieve the 1 ppb, sorry, I need a microgram sign there, 1 ppb SPLP for total mercury in the leachate. All right, in summary then, just to hit the high points, divalent metals can in fact be removed by precipitation as metal sulfides, metal carbonates, or metal hydroxides. The metal sulfide precipitation approach has important advantages, including much lower solubility of the precipitates and much broader pH range stability. These important characteristics give you comfort that you can achieve MCLs or SPLP or TCLP standards. The metal sulfide precipitation approach is widely applicable. It's a natural process. We're just enhancing it, speeding it up, making it more profuse, and adding on top of the metal sulfide precipitation, laying down iron sulfide precipitates on top of the precipitated heavy metals to lock them up. We achieve this by creating reducing conditions, ensuring an adequate supply of free sulfide, an adequate supply of free ferrous ion, maintaining pH in the optimal range, and I would add using reagents that provide the sulfate reducers with the simple organic carbon and phosphate that's essential to their activity. Use of these long-lasting reagents gives you that occlusion, that lockup that is so important, and our Metafix and Geoform reagents have proven very reliable in creating those kind of conditions to take out divalent heavy metals and achieve remedial objectives. All right, a few minutes remaining for comments and questions.